All right, the subject of today's lecture is molarity. Molarity is a unit of solution concentration favored by chemists. Molarity is represented by the capital letter M, and it is moles of solute per 1 liter of solution. This brings up what may or may not be two new terms to you. That's solute and solution. First of all, what is a solution? A solution is a homogeneous mixture, and homogeneous means it's uniform throughout, and it's uniform throughout on a molecular or atomic level. The classic example of a solution is salt water. If I have a container of water and I place table salt in it, I get a solution of table salt. So if I have this mixture here of salt and water, my solution has two parts. I refer to those two parts as the solvent and the solute. There are lots of creative definitions out there, let me tell you, for what a solute and a solvent is. You'll often hear the solute described as the minority component of a solution and the solvent as the majority. But most of the time, how I like to think of it is the solute is what you are dissolving, and your solvent is what you are dissolving the solute in. So your solution is two parts solute, what you're dissolving, and the solvent, what you're dissolving it in. So sodium chloride would be our solute, and water would be our solvent. So back to molarity now that we've defined our terms solute, solvent, and solution. And your solution, just to make things totally clear, your solution is the mixture. Your solution is your solute and your solvent together. Okay, so molarity, capital M, is moles of solute per liter of solution. So it's moles of the thing you're dissolving in the volume of the whole. One of the reasons molarity is so useful is, in addition to being a way of expressing concentration, it also provides a conversion factor. In this level of chemistry, whenever somebody gives you a unit of molarity, your first thought should be to think of that number as a conversion factor. For example, if I tell you you have a 0.30 molar solution of sodium chloride, then what you know is that 0.30 moles of sodium chloride is equal to 1 liter of solution. Now, most of the time, those of you who have lab know that we very, very rarely ever use a liter of solution. Most of the time, we're working units of milliliters. So I like to think of the conversion factor as being the number of moles, 0.3 moles of sodium chloride, related not to 1 liter, but to 1,000 milliliters of sodium chloride solution. So it provides a conversion factor between moles and volume. Now, we're going to use molarity in several different ways. But before we can use molarity, we have to learn how to make solutions and how to calculate molarity. So let's get to it. All right, what is the molarity of a solution made by dissolving 4.20 grams of potassium chloride in enough, and I don't know where I decided to spell enough that way, in enough water to make 250 milliliters of solution? Well, potassium chloride is our solvent, and we put that potassium chloride in 250 milliliters of solution. So we currently have units of grams per milliliter. I don't want grams per milliliter. I want moles per liter. So let's do the easiest first. Let's get rid of our milliliters. We know that 1 milliliter is equivalent to 1,000th of a liter. So I've placed my liters where they cancel out, my milliliters where they cancel out, and my liters where they'll be left on the bottom. So now I have units of grams per liter. I don't want grams per liter. I want moles per liter, so I'm going to have to place grams where they'll cancel out. I always know the relationship between moles and grams because my periodic table tells me. So I run to my periodic table. I see that my mass of potassium is 39.0983 plus 35.4527 gives me 74.551 grams of potassium chloride. So my grams of potassium chloride have canceled out, and I now have units of moles over liters. So I'm going to multiply everything on top, divide through by everything on the bottom, and that will give me 4.2 divided by 250 divided by 10 to the negative third divided by 74.55 equals, my calculator lie is 0.225352. However, I've got 1, 2, 3 sig figs there, 1, 2, 3, 4 sig figs there. 3 is my less number, so 1, 2, 3 sig figs. So my answer should be 0.225 molar. We would pronounce the unit molar, by the way. Yes, like the tooth, molar. So 0.225 molar potassium chloride aqueous solution. All right, a couple things to point out here when we look at this problem. And I'm going to do a little bit of cleanup here too, by the way. Notice the weird wording when you read this problem. And it wasn't a weird wording just because it was me. It's standard. What is the molarity of a solution made by dissolving 4.2 grams in enough water to make 250 milliliters of solution? Solutions are made in a piece of glassware known as a volumetric flask. A volumetric flask is a piece of glassware made to contain a certain amount of liquid. The volumetric flask has one calibration mark, usually on the neck, and that calibration mark tells you exactly how much liquid the flask contains. For example, if this was a 250 milliliter volumetric flask, when the water level rose up to that ring, and we go into this in more detail in lab, but when the water level rose to the bottom of that ring, your volumetric flask would contain 250.0, usually 2 decimals, 1 or 2 decimals, milliliters of solution. Solutions are made by taking your solute, for example, your 4.25 grams of potassium chloride, and putting that 4.20 grams of potassium chloride in the volumetric flask. Then, to that volumetric flask, you would add water. You would add enough water to make 250 milliliters of solution. You're saying, okay, why can't we just say that we'd add 250 milliliters of water? It turns out when you're mixing different substances, volumes are not additive. Remember, when you're dealing with matter, there's a lot of empty space. So a lot of times when you add a solute to a solvent, the attraction for those solute molecules will actually draw the solvent particles closer together. Sometimes it'll push it farther apart. But the point is the volumes aren't additive. You can see this really, really clearly. If you mix ethanol and water, if you mix 10 milliliters of ethanol with 90 milliliters of water, you'll wind up with less than 100 milliliters. Another classic, great, fun thing to do you can do at home is if you get a cup of water and begin shoveling in that sugar. I mean, really shovel it in there. What you'll notice is as you keep adding sugar, instead of your volume increasing, your volume actually decreases. So volumes aren't additive. That's why when you make a solution, you always do it following the procedure of adding your solute, then diluting with enough solvent to make your desired volume. And that will result in some funny wording to some of your homework questions. Whenever anybody talks about funny wording, I always think of Mary Poppins. I'm not going to have you write down supercalifragilisticexpialidocious, of course, because I can't spell that, but I can spell Mary Poppins. So why don't you write down Mary Poppins? All right, let's take a look at another example. Why don't you pause me and try this yourself? All right, did you pause me? I hope you did. Let's take a look at it together. What is the molarity of a solution made by dissolving 52.23 grams of disaccharide in enough water to make 500 milliliters of solution? So I'm going to start by setting up my line. I have 52.23 grams I don't want grams of disaccharide. Oh, and I have that 52.23 grams of disaccharide in a volume of 500 milliliters. I don't want grams of disaccharide. I can use my periodic table to calculate that 1 mole of disaccharide is 12 times 12.011 plus 24 times 1.0079 plus 12 times 15.9994, 360.314 grams of disaccharide. So now I've gotten rid of grams of disaccharide, and I've gone from grams per milliliter to moles per milliliter. I don't want milliliters, so I'm going to place my milliliters where they'll cancel out. And I know that 1 milliliter is 1,000th of a liter, 10 to the negative third there in case you can't read that. So now and that cancels out my milliliters. So now I'm left with units of moles per liter. Those are the units I'm wanting because that's the units of molarity. So I multiply everything on top, divide through by everything on the bottom. And that gives me 4 sig figs here, 4 sig figs there. So my answer with 4 sig figs is, not now R2, is 0.2899 molarity disaccharide aqueous solution. Chemistry's easy, life is hard. This can take a little bit of getting used to. Let's work one more problem. This way I'll work it a slightly different way for you, in case you're not liking my line. What is the molarity of a solution made by dissolving 0.034 grams of sodium chloride in enough water to make 10 milliliters of solution? We know we want units for our answer of moles of sodium chloride per liter solution. So what I can do is, rather than work it into the line, I can actually handle both halves of the problem separately. I can first solve for my volume. I have 10 milliliters of solution, and I know that 1 milliliter is 1,000th of a liter. So that means my volume in terms of liters would be, and I dropped a 0 there, would be 0.0123 liters. So I know that would be my volume. And then I can solve for my moles in a separate step as well if I wanted to. 0.034 grams of sodium chloride, and I know that 1 mole of sodium chloride is equivalent to how many grams? Go to my periodic chart, of course, 22.9898 plus 35.4527, 58.4425 grams of sodium chloride. So that gives me times 0.034. So that gives me 0.00058 moles of sodium chloride. I only have 2 sig figs there. So that's my moles. I want moles per liter, so now I just do a division step. Moles of sodium chloride per liter solution, 0.000582 moles of sodium chloride per 0.01000 liters, and that gives me a final molarity of 0.058 molar sodium chloride aqueous solution. So hopefully by now you've got the 2 ways we can work it down, and you're comfortable going from a mass of solute and a volume to molarity. What we want to try now is we want to try making our solution a different way. Up till now, we've only made solutions using a solid solute. Lots of things are actually maintained in the laboratory as concentrated solutions. The most common examples are acids. Acids are generally sold in and shipped in concentrated form. For example, hydrochloric acid is sold in a concentrated form, and that concentrated form has a molarity of 12.1 molar, meaning that hydrochloric acid has 12.1 moles of hydrochloric acid per liter. So whenever you want to make a solution of hydrochloric acid, you have to dilute the concentrated form. How do you dilute? How do you make a solution by dilution? Well, once again, you'd get your volumetric flask. And because we're dealing with a concentrated acid here, I'd put a little bit of water in first, or I'd always add acid to water or you'll be sorry. So I add a little bit of water. Then I add my acid. Add the acid I want to make the concentration I need, and then I dilute with my water once again to the volume that I want my solution to be. So it's basically the same procedure as we followed last time, with the exception of adding a little bit of water first for safety reasons. But dilution requires you to do either one of two things. You can handle the dilution of a concentrated solution either via formula or via stoichiometry. To handle it formalmatically, you would use the formula MCVC equals MDVD. In other words, if you get to know MCVC too well, you have to go see the MD about something. So that's the formula for handling the dilution of a solution. This is the molarity of the concentrated solution. This is the volume of the concentrated you'll need. This is the molarity of the dilute solution. That you're wanting to make. This is the volume of the dilute solution. So that's your formula for handling the dilution. So let's use this formula here. Let's bring it home and make it concrete here. How many milliliters of concentrated hydrochloric acid would I need to make (250 milliliters) of how many milliliters of concentrated hydrochloric acid would I need to make 250 milliliters of a 1.00 times 10 to the negative fourth molar hydrochloric acid solution? So there's our problem. Identify your numbers. I have a volume of a dilute solution I want to make. So that's the volume of my dilute solution. That's the concentration of the dilute solution I want to make, so that's the molarity of my dilute solution. I was given up here that concentrated hydrochloric acid has a molarity of 12.1, so that's the molarity of my concentrated solution. So now I can set up my problem. So I've got 12.1 molar times the volume I'm wanting to solve for equals, and I'm going to need more room here, times the concentration, and that's a 4, times the concentration of the solution I'm wanting to make, times the volume of it that I'm wanting to make. Do the algebra, and that gives you 1 second EE negative 1 times 250 divided by 12.1. That means that you'll need 2 point, and sig fig check, it looks like 3 here, 2.07 times 10 to the negative third milliliters of hydrochloric acid to make your solution. Chemistry's easy, life is hard. Let's try another. But before we try another, you know what was really hard? Life during the time of bed knobs and broomsticks. Why don't you write down bed knobs and broomsticks? Write down bed knobs and broomsticks. Alright, if concentrated sulfuric acid is 18 molar, how many milliliters of sulfuric acid do I need to make 100 milliliters of a 0.1 molar sulfuric acid solution? Alright, let's take a look and identify our numbers. We've got a molarity of our concentrated solution. I've got a volume of the dilute solution I'm wanting to make. I've got the molarity of the dilute solution I'm wanting to make. So now I just need to plug and chug. If I get to know MCVC too well, I have to go see the MD. So plug and chug here. 18 times the volume of the concentrated equals the concentration of the dilute times the volume of the dilute Now it's a matter of algebra here. So Vc equals 0.001 molar times 100 milliliters divided by 18 molar, and it looks like we're going to have 3 sig figs when we're all said and done here. 0.1 times 100 divided by, good grief, hit the wrong keys on my calculator there. It looks like we will need 0.556 milliliters of sulfuric acid. Chemistry's easy, life is hard. To use my dilution formula, strictly speaking, I don't have to have a concentrated solution. I just have to have a solution more concentrated than the solution I want to make. For example, a stock solution contains 0.1 molar nitric acid. How many milliliters of the stock solution would I need to make 200 milliliters of a 0.0250 molar nitric acid solution? This is my more concentrated solution, so I would make that my MC. This is still the volume of my dilute solution I'm wanting to make, the molarity of my dilute solution. So once again, we're in our MCVC equals MDVD pattern, where we have 0.10 molar times VC equals 0.0250 M times 200 milliliters All right. Multiply everything on top, divide through by everything on the bottom. You know the drill. And we're going to need much more this time. It turns out we're going to need, oh, it looks like we only got 2 sig figs there. We're going to need 50 milliliters of our stock solution to make our dilute solution. All right, chemistry is easy, life is hard. Let's keep moving. One of the reasons that we're so interested in molarity is we want to use molarity to help us with stoichiometric calculations when it comes to reagents in the laboratory that are usually stored as solutions as opposed to gram amounts. For example, it lets me answer lots of questions such as, if I react 25 milliliters of 0.1 molar sodium hydroxide with excess sulfuric acid, how many grams of sodium sulfate are produced? For the first time in a long time, you're looking at a problem where you don't have an amount of grams. Not only that, but you have 2 numbers. Remember, I said at the beginning of this lecture, whenever you see molarity, you should always instantly think conversion factor. So whenever I see molarity in a problem, what I instantly do is I rewrite it. It says I've got 0.01 molarity sodium hydroxide. Well, what I'm going to do is I'm going to rewrite that to say 1 mole of, whoops, not going to say that. I'm going to rewrite that to say 0.10 moles of sodium hydroxide is equal to 1,000 milliliters of sodium hydroxide solution, and use that as a unit conversion somewhere in my problem. Since I've identified molarity as a unit conversion, that means I only have one number in my problem that I can start my line with, my 25 milliliters. So that's exactly what I'm going to do. 25 milliliters of sodium hydroxide. I don't want milliliters of sodium hydroxide, so I'm going to place milliliters of sodium hydroxide where they'll cancel out. So I've got 1,000 milliliters sodium hydroxide, 0.10 moles sodium hydroxide is equivalent to 1,000 milliliters sodium hydroxide. So I've canceled out my milliliters of sodium hydroxide, and I've gone from units of milliliters of sodium hydroxide to moles of sodium hydroxide. Now, I don't want moles of sodium hydroxide in this problem. That's not what they're asking for. So I'm going to get rid of moles of sodium hydroxide. What do I know about moles of sodium hydroxide? Well, according to my chemical equation, for every 2 moles of sodium hydroxide I consume, I produce 1 mole of sodium sulfate. So now I have moles of sodium sulfate. Do I want moles of sodium sulfate? No. So I'm going to place moles of sodium sulfate so that they cancel out. I want grams of sodium sulfate. My problem keeps getting smaller and smaller and smaller. If only life worked that way. I go to my periodic table and I calculate the mass of my sodium sulfate. 2 times 22.9898 plus 32.066 plus 4 times 15.9994, and that gives me 142.043 grams of sodium hydroxide. So I've gone from milliliters of sodium hydroxide to moles of sodium hydroxide to moles of sodium sulfate to grams of sodium sulfate. And when I went from volume to moles, I used molarity as my conversion factor. Oh, whoops, an answer would be helpful, wouldn't it? And that gives me 1.78 grams of sodium sulfate. Chemistry is easy, life is hard. All we're doing with molarity is in the past, where in our grams of A, moles of B pattern, we would have that unit of molar mass. We're now changing it to molarity. In other words, if I were to summarize, I'd say we can form a new pattern here where we have milliliters of A and we can go to moles of A using molarity. We can go from moles of A to moles of B using a chemical reaction. And then we could actually go to a volume of B as well, milliliters of B, using molarity if we wanted to. Let's take a look. How many grams of lead-2 iodide can be formed by reacting 38.2 milliliters of 0.1 molar potassium iodide with excess lead-2 nitrate? Well, it helps if we have a chemical reaction to go off of. So let me write that for you there. 2 potassium iodides aqueous react with lead nitrate, also aqueous, to yield lead iodide solid plus our spectator. Plus 2 units of potassium nitrate aqueous. Once again, we're looking at a problem where we see molarity, and whenever you see molarity, I always instantly label that molarity as a conversion factor. So since I see 0.1 molar potassium iodide, right away what I'm going to do is I'm going to say, okay, that means 0.10 moles of potassium iodide is equal to 1,000 milliliters of potassium iodide. So since I've labeled my molarity as a conversion factor, that means I'm going to start working my problem with my other number, my 38.2 milliliters. So I have 38.2 milliliters of potassium iodide. I don't want milliliters. I want to get rid of milliliters. I know, because of my molarity, the relationship between milliliters and moles of potassium iodide. So I'm going to place milliliters where they cancel out, and And I know that 1,000 milliliters is equal to 0.10 moles of potassium iodide. I don't want moles of potassium iodide. I want moles of lead to iodide. My chemical equation gives me the relationship. 2 moles of potassium iodide produce 1 mole of lead 2 nitrate. I place moles of potassium iodide where they cancel out. I don't want moles of lead 2 iodide, I want grams of lead 2 iodide. According to my periodic table, 1 mole of lead iodide has a mass of 207.2. Come on, turn on. Lead. 207.2 plus 2 times 126.9045 gives me 461.0 grams lead iodide. So now I've canceled out my moles of lead iodide, and if we were flowing along up here, I've gone to moles, lead iodide, and then from moles of lead to iodide, I've gone to grams of lead 2 iodide. I multiply everything on top, divide through by everything on the bottom. I'm hoping you're working along with me here. And that gives me let's see, 3 sig figs, 2 sig figs, 0.88 grams of lead iodide. So chemistry's easy, life is hard. This is the exact same thing we've been doing for quite some time now, except that instead of using molar mass to go from grams to moles, you're using molarity to do the same thing. Now we can have molarity on both ends of our solutions. Of our problem. This often occurs when we're working a type of problem known as titration problems. Why don't you write down Herbie the love bug? Write down Herbie the love bug. Herbie the love bug. I'm hoping you're writing down Herbie the love bug. Alright, now we're ready to talk about titrations. If you've had high school chemistry, you probably are familiar with titrations and may have even done one before. A titration is a way of using a titration is an experimental technique of using a solution of known concentration referred to as the titrant, to determine the concentration of an unknown solution. Known as the analyte. So terms there, titrant and analyte. Titration is an experimental technique of using a solution of known concentration, referred to as the titrant, to determine the concentration of an unknown solution, referred to as the analyte. Most titrations are carried out using some simple pieces of glassware. The first of these pieces of glassware is a burette, and I've attempted to sculpt one here. If you're taking the lab class, we'll go into this into gory detail. But you have a burette, And in this burette, you place the titrant, the solution whose concentration you know. And a burette's purpose is to measure a volume of titrant. Then you have a flask, usually below the burette, and in this flask you have your unknown solution, but you know the volume of this solution. Unknown concentration, but you know its volume. The easiest way to talk about titration is actually to walk you through a problem. So let's take a look at a simple problem. All right, I have my burette, and in my burette I have a solution whose concentration I know. I'm going to make it 0.205 molar hydrochloric acid. Below my burette, I have a solution whose concentration I don't know. I know my solution, however, is sodium hydroxide. I also know that I have 10 milliliters of my unknown sodium hydroxide solution. Also in my burette, I'm going to place what's known as an indicator. This indicator is going to change color when the molar quantities of sodium hydroxide and hydrochloric acid are equal. If I don't want to use an indicator, I could use a pH meter. There are several ways I could determine the end point of this titration. There are some more terms in here that we'll go into again in gory detail in lab, but for our purposes, we've got our experiment set up, and we conduct our experiment, slowly adding a drop of our time of our hydrochloric acid to our sodium hydroxide solution. It turns out it takes 15.44 milliliters of 0.0205 molar hydrochloric acid to completely react with 10 milliliters of my unknown It takes 15.44 milliliters of 0.025 molar hydrochloric acid to completely react with 10 milliliters of my unknown hydrochloric acid solution. What is the concentration of the sodium hydroxide? So once again, we've got number overload. The first thing I want to do is I want to identify one of them as a unit conversion if possible. And molarity always tells me the way. It tells me that 0.0250 moles of hydrochloric acid, in this case, is equal to 1,000 milliliters of hydrochloric acid. That's supposed to be a 3 again. I swear I can't make 3 with this 3 with this stylus. So that leaves me with two other numbers in my problem. We've got 15.44 milliliters of my hydrochloric acid. So that 15.44 milliliters is defined. if we read on and we look at my 10 milliliters, it says 10 milliliters of an unknown solution. And we want to know the concentration of it. In order to figure out the concentration of sodium hydroxide, I need to figure out the number of moles of my sodium hydroxide in that 10 milliliters. So what I'm going to do is I'm going to set aside that 10 milliliters. Since it's undefined, right? I have 10 milliliters, but 10 milliliters of what? Since that 10 milliliters is undefined, I'm going to start my line with my 15.44 milliliters. So I'm going to say that I have 15.44 milliliters of my hydrochloric acid. I don't want milliliters of hydrochloric acid, so I'm going to place milliliters of hydrochloric acid where they'll cancel out. I know the relationship between milliliters of hydrochloric acid and moles of hydrochloric acid. I know that for every 1,000 milliliters of hydrochloric acid solution I have 0.025 moles hydrochloric acid. I have moles of hydrochloric acid, but I don't want moles of hydrochloric acid. According to my chemical equation, oh, and it would be nice if Dr. Kelly had given you a chemical equation, yes? Hydrochloric acid plus sodium hydroxide reacting in a 1-to-1 ratio give you sodium chloride and water. But according to my chemical equation, for every 1 mole of hydrochloric acid I have 1 mole of sodium hydroxide. I now have the units I'm looking for. I now have moles of sodium hydroxide. So I can multiply everything on top, divide through by everything on the bottom. And when I do that, I get 15.44 times 0.0250 divide by 1,000 equals 3.86 times 10 to the negative 4th moles of sodium hydroxide. Now I'm not done, because the problem wants to know the concentration of my sodium hydroxide. Whoops. So concentration is always moles per liter. I know that these 3.86 times 10 to the negative 4th moles of sodium hydroxide were dissolved in 10 milliliters of sodium hydroxide. Now, molarity is not per milliliter, it's per liter, so I'm going to have to do a unit conversion and cancel out my milliliters. I multiply everything on top and divide through by everything on the bottom, and my molarity winds up being 0.0386 molar, because I have units of moles per liter. If I was to define this as a two-step process, here's what I would tell you. 1. Calculate your moles of unknown. Then 2, calculate your concentration. And you're going to calculate your moles of unknown by going from milliliters of A to moles of A using the molarity of A. Then you're going to go from moles of A to moles of B using a chemical reaction. Then you're going to calculate your concentration by taking your moles of B and dividing by the volume in liters of B. And that's going to be your 1-2 Texas two-step process. Let's do another example. All right, let's take a look. It takes 42 milliliters of a 0.00150 calcium hydroxide solution to completely react with 50 milliliters of an unknown phosphoric acid solution. What is the concentration of the phosphoric acid solution? All right, we've got a lot of numbers here. Remember, we want to find a unit conversion first. So we've got a molarity that tells us there are 0.00150 moles of calcium hydroxide, and that's equal to 1,000 milliliters of calcium hydroxide. Then, if we continue reading, we see that we have a volume linked with that unit conversion. It's related to 42 milliliters. Then, we have 50 milliliters of an unknown solution. So our 50 milliliters is undefined, meaning we can't start with it. What we're going to have to do is we want to figure out, in this question, is we want to figure out the number of moles of phosphoric acid in that 50 milliliters. So my first step is going to be to calculate my moles of phosphoric acid. To do that, I'm going to use my line method. Remember, I'm setting aside that 50 milliliters for step 2, which means that my starting quantity is going to be my 42 milliliters. How do I know it's my 42 milliliters? Again, just to reiterate, it's linked to a unit conversion that I already have, so that's how I know I want to start with it. If I started with my milliliters of phosphoric acid, I couldn't do anything. I have 42 milliliters of calcium hydroxide. I know that 1,000 milliliters of calcium hydroxide is equivalent to 1.50 times 10. Went to scientific notation there because I got tired of saying all the zeros. Moles calcium hydroxide. I now have moles of calcium hydroxide, but I don't want moles of calcium hydroxide. I want moles of phosphoric acid. According to my chemical equation, for every 3 moles of calcium hydroxide I react 2 moles of phosphoric acid. So 3 moles calcium hydroxide is equivalent to 2 moles phosphoric acid. Canceled out the milliliters. We have moles. So I multiply everything. That leaves us with, whoops, I forgot to write my units there, moles phosphoric. So I'm going to multiply everything on top, divide through by everything on the bottom. And when I do that, whoops, in case you couldn't tell, I just dropped the iPad. So I multiply everything on top, divide through by everything on the bottom. 42 divided by 1, 2, 3 times 1.5 second EE to the negative third divided by 3 times 2, and that gives me, oh, haha, I should have been able to do that in my head. 4.2 times 10 to the negative fifth moles of phosphoric acid. So that's my step 1 answer. I'm wanting the concentration of that phosphoric acid. So my step 2 is to calculate the molarity. And to do that, I'm taking my number of moles and I'm placing them in their volume. And I know that they're in a volume of 50 milliliters because that was given to me in the problem. Oops. My heart's racing from dropping the iPad there. I want to get rid of milliliters because I have to have liters on the bottom. Multiply everything on top, divide through by everything on the bottom, and I wind up with 4.2 times, whoops, no, that's not right. I'm going to use my calculator here. It should be 2.1 times 10 to the negative second. But the rate I'm going today, ever had one of those days? Well, I'm having one of them now. And some of you are saying, yes, we have those days. They're called test days. All right, 4.2 second negative 5 divide by 50 times 1,000. Oh, and you get 8.4 times 10 to the negative 4th molar phosphoric acid. And there's your answer. That's it for this lecture. Feel free to ask questions. I know I went through this relatively quickly. You're saying, wait a second, it took over an hour. That's still relatively quickly for the amount of things we did with this. So by all means, ask questions if you have them. I'm here for you, wanting to help.